In this video, we're going to look at the graph of the cosecant function. And to start off with, I'm just going to go ahead and use the calculator to look at the graph, and then we will come back and kind of describe what's happening here with the graph. So if we go to y equals, and if we're going to try to look at the graph of y equals the cosecant of x, then what we have to remember is because the calculator doesn't have a cosecant key, we're actually going to type in, this is the reciprocal for sine, so we're going to use y equals 1 over the sine of x. So if we go to the calculator, we would go y1 is equal to 1 divided by the sine of x. And we want to make sure, in this case, that we're in radian mode. So if you go to your calculator, I am in radians. And then if we go to zoom, I want to go to zoom 7 so that we're in trig form. So zoom 7. And here we have our graph for the cosecant function. And this looks a little bit different than what we had before with the sine function. So if I copy this over, we can talk a little about what's happening here. You'll notice, once again, because we went to zoom trig, then we're starting here at 0 and going over to 2 pi. So therefore, this would be pi over 2, pi, 3 pi over 2, and 2 pi. And what's happening, you can kind of see that just like the sine function, this graph is also repeating. And you're going to notice if we start at 0, the graph is going to come down and then go back up. It almost kind of looks like a parabola here. And then at pi, the graph is split. There's a break in the graph at pi, and then it opens down, comes up here, and then there's another break at 2 pi. And if we even look at 0, there's another break at 0 as well. So we're ending up with, at pi, 0, and then if we go over here to the negative side, this would be negative pi over 2, or at this point this would be a negative pi, negative 3 pi over 2, and negative 2 pi. So even at negative pi here, we have a split in the graph. And what we have here are vertical asymptotes that we talked about last semester in pre-calc 1. And the graph is splitting here. Now, why do we have a vertical asymptote? Well, if we think of our unit circle, then we know that if we kind of go around and look at these key points, at 0 here we have 1, 0, top of the circle. If we go around here from 0, pi over 2, pi, 3 pi over 2, and all the way back to 2 pi, if we look at our coordinates here, then we're going to notice what's happening, hopefully. So if we look at this point here at 0, we have a vertical asymptote, because remember, what is the cosecant? Well, it's the reciprocal of our sine. So when we're looking at trying to calculate the cosecant, if we try to take, for example, here, y equals 1 over the sine of 0 radians, and sine is our y value. So right here we have a y value of 0, which means we're going to have 1 over 0, which is undefined. So because we can't divide by 0, that's why we have this vertical asymptote at 0. And then at pi over 2, we're okay because we have a 1, but then when we come over here to pi, notice again, we're looking at our y value, we have another 0. 3 pi over 2, we're okay because y is a negative 1. And then back to 2 pi, we have y is 0. So therefore, that's why at 0, pi over 2, and then of course if we went negative, we would still have a vertical asymptote at negative pi as well as a negative 2 pi. So all of these points here on the graph, your y coordinate is 0. So anytime we have 0 as our y coordinate, then we're going to end up with this division by 0, which is going to be undefined. Okay? So now let's look at how does this compare to the graph of our sine function. Okay, well, let me scroll down here a little bit and let's graph now. Go back to the calculator. I'm going to leave 1 over sine x here. And notice what happens if I go to y2 and we actually look at the sine of x. And if I hit graph, notice here we're tracing out the sine function and it's actually kind of going up and touching the graph of our cosecant. So let's see if we can make some kind of conclusion based on this here. If we notice the points here, whoops, let's use our red marker here. If we have a vertical asymptote at these points that we talked about before, notice what's happening to the sine function at these points. That's where our sine function, okay, so if we look at the graph here, this is the graph of our sine function. So notice the y equals sine x. When it crosses the x-axis, that tells us the function is equal to 0, and that's why for our cosecant function, that's why you have vertical asymptotes for y equals cosecant x, because again, remember this is really 1 over the sine of x. So if the sine of x is 0, our cosecant function is undefined. Now, typically what I suggest is if you want to graph the cosecant function by hand, all you have to do is think about in the previous videos, how did we graph our sine function? Well, if you graph the sine function, just like we did in the past, then in order to graph the cosecant, then all you have to do is kind of where you have a peak for your sine function, that's where you're going to kind of have the low point for the cosecant, and wherever the sine function crosses the x-axis, where it's 0, that's where you're going to have a vertical asymptote. So every point where it crosses, you know, for the cosecant, there's going to be a vertical asymptote. And if you think of your sine function, everywhere you have a peak, you're going to have kind of the low part of the graph. And then everywhere you have a valley, you're going to have the part of the cosecant that's opening down that comes up and touches at this valley of the sine function. So notice here again, it's going to be a periodic function just like sine. So it's going to repeat. So if we were looking at calculating the period, we would do this the same thing we did with the sine function. In this case, we could calculate the period. Remember, we said that it would be 2 pi over b. Well, if we go up here, b was the coefficient of our x, so the coefficient of the x is understood to be 1. So therefore, the basic cosecant function would be 2 pi over 1, which is going to simply have a period of 2 pi. So that means as we start from 0 and we go out to 2 pi, it takes 2 pi in order for the graph to repeat. So here our graph goes up, then it curves down here at the bottom, and then at 2 pi here, if we were to continue to look at the graph of the cosecant, then it would then have over here a graph like this where it would start to repeat itself. So the techniques we used before with the sine function, we would use the same thing that we did before. Now, the one thing you'll notice, we talked about the sine function actually had an amplitude, and the cosecant, because of the type of graph we have, the cosecant does not have an amplitude. But as far as the phase shift and so forth that we talked about, that's going to still be the same way that we can calculate like we did the sine function. So for example, if we want to change the period, let's look at the graph of y equals, let's say, the cosecant of 2x. Well, right off, if we want to look at what the period of this particular function is going to be, remember we would simply take 2 pi over b. So for this it would be 2 pi over our 2, that's our b value. So 2 pi over 2 is simply going to be equal to pi. So if we go to the calculator now, go to y equals, and I'll leave the sine function here, and I'm going to type in for y1, 1 over the sine of 2x, and let's see what effect that has. And it should, based on what we came up with here, our period is going to be pi, whereas the initial period was 2 pi. So that means when we see this part of the graph here and here, instead of taking a distance of 2 pi, it's only going to go out to pi. So we should actually see the graph go up, down, and then up and down from 0 to 2 pi. So we're going to end up with 2 full periods from 0 to 2 pi, hopefully. So let's see if we did the calculations right. So 1 over sine of 2x. So if we kind of start here from 0, there's our one period, and then there's the second period. And again, we can see here, this is the graph of our sine, so we can see that the graph of the sine is only representing here one period. So let's go back and adjust it as well. If we made this y equals the sine of 2x, and then once again we'll notice when the sine function is graphed, watch how it's going to come up and touch the low point, and then it's going to touch each of these points as it goes across here. So now if we compare this, and maybe let me take out the sine function so we can just look at the cosecant. So let's copy this over. So here we have our y equals cosecant of 2x. So this is still going from 0 to 2 pi. But now what we're going to notice is this point here is pi over 4. Okay, and then this would be 2 pi over 4, 3 pi over 4, 4 pi over 4, 5, 6 pi over 4, and 7 pi over 4, and of course 8 pi over 4 would be 2 pi. So what we're noticing is if we start at 0, and here's the graph of our cosecant, that's going to give us from here to here, which is 4 pi over 4, that's going to give us one period. So from 0 to pi, we're ending up with one complete period of this graph. So therefore, that's why over here, we calculated the period of the function to be equal to pi, which means that takes it a period of 1 pi before the graph starts to repeat itself, because once we get to this point here at 4 pi over 4, which is 1 pi, our graph starts to repeat itself. And of course, if we went to the left, you would get the negative. So again, this would indicate here one period. So here, if we look at this total, we have 1, 2, 3, 4 full periods of this graph throughout from the negative 2 pi to a positive 2 pi. And we'll notice, has the graph been shifted any to the left or to the right? And the answer is no, because here all we did was, in this case, affect the period. All right, so there, hopefully you have a little bit better understanding of looking at the graph of your cosecant function. And keep in mind, if you know the graph of your sine function, then you could certainly find the graph of your cosecant. So let me look at one other quick example. If we had y equals, let's say, the cosecant of x plus pi plus 1. Now, just like we have done before, if we go to calculate the period, the coefficient of the x here is 1, so that would be 2 pi over 1, which is equal to 1. And if we want to look at the phase shift, we would take the x plus pi that's in parentheses, set that equal to 0, and we get x equals a negative pi. And then, of course, the plus 1 says the graph is going to be moved up. Because it's positive, it'll go up 1 unit. So let's see if that happens to be the case. So if we look at the cosecant of x plus pi plus 1. So in order to type that in, we're going to have to do 1 divided by the sine, okay? And this would be x plus, and what do we have here? Plus pi. So 1 over the sine of x plus pi, close the parentheses, okay? And then we want to add a plus 1. So then if we look at the graph, now notice what's happened here. Because of the plus 1, notice where this bottom graph, the top part of the graphs here, where they normally, this peak would come down here to 1, everything's been moved up. So that's why the graphs on the bottom, they've been moved up 1. So that's why now these points here are actually touching the x-axis. They used to be here at -1, whereas this point used to be down here at +1. So everything has been moved up 1. Okay, so when we look at this, our x-axis, you can kind of think of the axis for where we're going through is now moved up here to a +1. And then, of course, we'll notice we had the x plus pi, so x equals negative pi. So here, the graph has been shifted pi units to the left. So for example, let's see if this is going to look too bad. If we were just to look at the graph of y equals sine of x, so in other words, I'm sorry, we want to make it cosecant. So if we looked at 1 divided by the sine of x. So here I want to look at just the cosecant function and see how it's been moved in relationship to the cosecant of x plus pi plus 1. And let's see if this doesn't look too bad to look at. So if we look at the graph, so notice here we now have the plane cosecant. So let's copy this over. So the graph of y equals cosecant x, that would be this graph here. And then if we look at the graph of the one we have up here above, this one, which is the cosecant x plus pi plus 1, that's going to be the part here in red. So we can see the effect that it's having here. We notice that the period is still 2 pi. And what we've done is this graph has been moved up 1 on the y-axis. So that's why here you can see that in the purple, the graph was here, but now everything's been moved up 1, so we can see that this point has now gone to here, so we can see how those points have changed. And whereas this point is here. And also it's been shifted, we can see here in the green, it's been moved a negative pi, so it's pi units to the left. So that tells us that this point, if it's been moved, it is now located here. Okay, and just like this point has been moved to here. So we can actually see that phase shift of moving pi units to the left and moving 1 unit up on the y-axis. All right, so hopefully now you feel pretty good about graphing the cosecant, and just keep in mind the cosecant is simply going to be the y equals 1 over sine of x.